All right, guys, in this video, we are going to finally finish our heat energy chapter. So far, we have talked about all about heat, and we have found the delta H, so the enthalpy of reactions, again, the heat of a reaction, and figuring out whether that reaction's endothermic or exothermic, how that heat was transferred in that whole process. So we found the enthalpy of reactions from or by calorimetry. And that's what you have a quiz on next week, next Tuesday on the 31st. So again, finding the heat of the reaction through calorimetry, we organized our information to two separate columns to see how the heat was flowing. You could find the heat on one side, and we brought it over to the other side, just switching our signs for heat because heat lost equals heat gained. And then again, working with our enthalpy units, we are always finding the heat per mole of a substance in that reaction or solution process. So that's one way that we did that. Another way we found the heat of a reaction in last lecture was Hess's law, where we summed up little smaller elementary reactions so that they would add up to an overall, kind of like putting a puzzle together, where you have to manipulate your puzzle pieces, reverse them, maybe double them, maybe triple them, maybe cut them in half. You could even multiply by 1/2 if you needed half of your recipe, just like you would do in cooking. And then in today's lecture, we are going to, so this is today, we're going to finally find the heat of a reaction using heats of formation, or using these standard heats of formation. Okay, so let's do that in our packet that you guys should all have. Okay, so we're down here at the bottom. So here it says the standard enthalpy of formation for a compound. Notice I have that starred and underlined. What does the word formation mean? Okay, formation means to form. We form chemical compounds. We're not forming elements. Our natural elements already exist in the world. And for this class, you're assuming that, again, all the elements already existed. We're not taking into consideration any exceptions like diamond. Diamond is elemental carbon, but it does have a small heat of formation because it's in a more geometric shape. So you could actually look those up in your text in the index table of all these heats of formation. So the standard enthalpy of formation for a compound is what we're going to be using. Okay, so again, it's the energy that is produced or released in that formation. Of the compound. Okay, the heat of formation for elements equals 0 kilojoules. So you need to make sure that you know that. They're not going to tell you that in any problems. It's just assume that you will know that elements have a value of 0 for their heat of formation. Now, how do we find the overall change in a reaction? Okay, well, the change of reaction is kind of like changing the temperature. We're always looking at the final state minus the initial state. And we talked about in class when we were all together how important it was to do final minus initial, because that will give you the direction of your heat flow. There is a big difference between a negative and a positive number when dealing with heat energy. So we have this equation here. The overall heat of a reaction is equal to the sum of the enthalpies of the products minus the sum of the enthalpies of the reactants. Now, the only thing missing in here, and there's different ways to kind of write these things out, is I forgot my little N value. And we know what N means from our gas law chapter. N is the symbol for moles. Okay, so that's what I'm indicating down here. It says careful. Heats of formation are given in kilojoules per 1 mole. So if you have more than 1 mole in a balanced equation, what do? You need to multiply. Okay, so that's going to be really important, and we're going to check that out on the other page. So let's flip. All right, guys, so we're given a nice balanced equation, which was already great. And notice they gave us some heat of formation data already in our chart. And you've got your sheet at home, but kind of zooming in right there. That's what we have. Notice one of those values is positive for the heat of formation, and the other two are negative and exothermic. Okay. Now, looking at our balanced equation, do we see any elements up there? See, there's a compound. Is that a compound or an element? Remember, that's a diatomic element. So I'm going to go ahead and cross that out because it's an element. Okay, so its value for its heat of formation is 0. And I'm just going to cross it out because I don't want it to bother me in any way working this problem here. Okay, all right, and then we've got our two products that are also compounds. So the question says calculate the heat of the reaction using our enthalpy of formation information below. And if some people, again, are wondering what that little circle dot is right there, that's just telling you that it is a standard heat of formation, and it was measured under standard conditions, 25 degrees Celsius, I believe. You could look up those exact values for the standard case, slightly different than our standard STP that we're talking about for gas laws. But again, all these numbers could be found in an index of heats of formation. Alrighty, so we need to find the heat of the reaction. So we need to do, basically in a nutshell, our products minus our reactants. Now, I just like to write a very generic form right here, keeping in mind we need to do the sum of the products minus the sum of the reactants. Now, where are our products? Okay, because people always make errors here. A common mistake is mixing up our products and our reactants, which would give an incorrect answer. So these are our products up here, and these are our reactants up here. Okay, so now that I've sort of organized my thought process, we can go ahead and do that. So we need the sum of the products. So we have two different products. And notice there's not 1 mole of each. There's 5 here and 9 here. So we need to take that into account because that standard enthalpy of formation is per 1 mole. So looking for my B2O3 right there. Okay, I have 5 moles of it. Times negative, keeping track of those negatives, so I'm going to circle it. This is kilojoules over 1 mole. If you want to put that 1 in there, you can. So that's my first product. Now, I need to add it to my second product because this is the sum. And we have 9 moles of that, of our water vapor. And then we've got negative 241.82 kilojoules per 1 mole. Okay, this is our products. So we've got the sum of the products minus, and I'm running out of space here at home, the sum of the reactant. So we just have one reactant to worry about. Okay, so I'm going to kind of put that down here because I'm running out of space, and we have 2 moles of it. Times, okay, where is it? 73.2, and it's positive, kilojoules per 1 mole. Alrighty, so sorry, I kind of smushed that in there, but again, I think you're following along just fine at home with your packets. Making do. We're doing the best that we can. And now we're going to do the math. Now, I'm not going to overload my calculator. I'm going to write just in pieces. So 5 times our negative 1272.77. Okay, so that's giving me a value of negative 6363.85, and that's simply just kilojoules, plus the next one, negative 2176.38 kilojoules. Again, our moles canceled out. So we have all of that. And then we need to subtract it. So minus, I'm going to go ahead and multiply that out, our positive value, which is now a negative because we don't want to forget this minus, and then this in here was positive. So minus 146.4 kilojoules. Okay, sometimes it's nice to work in different colors. So we have this big expression right here. So again, these were the sum of our products. We could add those two together, have a nice big negative number. And then we're subtracting out this number here. So it's going to make it an even larger negative number. So again, if we add this all up, what is our answer going to be here? So let me go ahead and do that. And remember, you guys are supposed to be doing it at home. Make sure I don't make any math errors, just like in class. Okay, so I'm getting a total value, my delta H of the reaction. And again, this is for question number 1. I'm going to let you work on the other one. Is equal to negative, really big number. So we've got a nice combustion reaction, 8686.63, and this is simply kilojoules. Again, why not kilojoules per mole? Well, our moles canceled out in here, and since we have that delta H of this overall reaction up here, you could put this value of heat over any molar quantity in this problem. So using your enthalpy as a conversion factor like we've done before. So let's look at this second problem. In the beginning of our heat packet, we did something similar. So calculate the heat given off in kilojoules when only half a mole of B5H9 reacts. So the delta H of this reaction, we already calculated. It says that when you do this complete recipe here and you burn 2 moles of B5H9, you're going to get 8,686.63 kilojoules of heat released. Well, they want to know how much heat's released if you only have half a mole. So let's start with our half a mole. And how would we express that on a piece of paper? Well, we're going to create our own conversion factor. So what does our balanced equation say? It says that, again, 8,686.63 kilojoules is released for how many moles? For 2 moles of B5H9. Okay, so we made ourselves a conversion factor from our balanced equation like we've been practicing. Okay. So now let's multiply that out. Because if we just wanted a small energy output, we wouldn't want to waste fuel, right? It's really important. Some people are like, what's the point of all these things? We don't want to be wasteful in the world, right? We only have a certain abundance of so many things. And if everybody was just constantly using everything in excess, it wouldn't make that world a very good place, right? We're struggling with all kinds of things right now. And people, using too much of what they shouldn't. So these are important things to keep in mind, even in chemistry calculations. Okay, and some of you are like, oh, sig figs, okay, which is so great. So again, I'm getting this many kilojoules. For those of you at home still practicing those sig figs, that's awesome. Looking at this value we started with, 123. So technically we would write negative 2170 kilojoules. Okay, and have our 3 sig figs there. Alrighty, so I want you guys to try this next one at home. Same way here, identify any elements that might want to cross out so you can ignore in your calculations. Make sure you know the difference between reactants and products. And then here is a special little one I'm going to leave for you to do as well. So something that we're finding out slightly different is that you've got the heat of formation for nitroglycerin that you're calculating for that compound right here, the reactant. We don't know that, okay? They did give you the overall change in energy of the reaction. which we solved for in our previous problem up here. So they're asking for something different, okay? They didn't give you the heat of formation of the reactant, so you're going to need it to be a variable. So we're going to go ahead and set it up in this video, and then you've got to do your algebra. Okay, so again, thinking the delta H of our reaction is equal to the products minus the reactants. Okay, so that's what we're thinking there. These are our products. This is our single reactant right there. Okay, crossing out any elements so we don't have to worry about them. Compound, 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 element, element, which is good because some people go, well, how come they didn't give us the heat of formation of those? Well, they're elements. It's 0. So we need to realize that and commit that to our memory bank. And they did give us the heat of the reaction, so we can put that value already right here. So negative 5,678 kilojoules is equal to our products. We do have 2 products, so just like we did before, we have 12 moles of the CO2, and they gave us its heat of formation. They said it's negative 393.5 kilojoules per 1 mole. And we need to sum that to our second product. Okay, so we have 10 moles of water times negative 241.8 kilojoules per mole. So those are the products. And then our reactant. Well, don't forget, some people just go minus X. Well, we don't want just minus X because we have four moles of it. So just like we did here, moles times heat of formation, moles times heat of formation. So now we've got to subtract out, and we should have 4 moles times X, right? So again, our X is what we're solving for. We want to know the heat of formation for our nitroglycerin. So we've got 4 moles X, or minus 4X. So you need to solve for X. So see if you can do your algebra at home. Remember, you want X on one side of the equation, and your X final unit should be in kilojoules per mole when we divide by that 4 moles. So we should have kilojoules per mole for that heat of formation. Okay. All right, guys, this is the end of chapter 6. Don't forget, you've got a calorimetry quiz next Tuesday. So make sure your computers are all up to date. Make sure you've checked out the videos on enabling Flash, although I have also been able to make different quizzes now that you shouldn't have to worry too much about that. But again, don't ignore it. Make sure you know how to enable Flash on your computer just in case, or how to unlock it. So I sent you an announcement with some helpful links to do that as well. So make sure you do that, and then we should be good to go. So finish up your heat energy homework on sapling. Make sure you don't forget that you've got a second opportunity to take the gas law quiz tomorrow. And of course, you've got a calorimetry quiz on Tuesday the 31st, scheduled for class time only, right? Everybody's taking it like normal class time at 11:30. I keep sending you reminders, so hopefully you are getting all those. And I understand you're getting a lot of emails from lots of teachers. Well, that's the world we're in right now. Everything's online, nothing's face-to-face. So at least we have this opportunity to keep going to school. So that's what you got to keep in mind. So that is our world for the time being. You are living in a small piece of history, which will just be a tiny piece of your history when you're much older. I will talk to you guys soon. Hope you're doing fantastic. Okay, bye.